All right, now that we are solid on our oxidation numbers, we're going to switch to another idea, which is standard reduction potentials. Now, standard reduction potentials are listed in a table of all the half reactions written as reductions. So if you look over here, right, so this is my standard reduction potentials of half cells at 25 degrees Celsius, which always makes me think about how complicated chemistry must be, because what about 26 and 27 and 28? We're only given this one table. But anyway, so all of these reactions are the half reactions. So this is the reduction of fluoride, free fluoride, to a fluoride ion. This is S2O8 as a reduction to SO42 minus or sulfate, and so on and so forth. So the way that this table works is that it shows the potential for a species to gain electrons and be reduced or act as an oxidation or an oxidizing agent. So you'll notice on the left-hand side, there is an arrow and it shows the strength of an oxidizing agent. So at the top, these guys have the most tendency to be reduced. And then the ones at the bottom have the least tendency to be reduced. Now, when you're looking at this is all in the note, I should just go in order, but it is showing everything in terms of this e to the exponent 0, which is called the electron, all of a sudden I'm losing my word. It is like the voltage, okay? It's the standard potential of a cell. And so that'll make more sense when we put these together and make these electrical chemical cells. But for now, the key point of this table is that on the right-hand side, you have this E value, which is measured in volts, and it is going to be talking about its tendency to gain or lose electrons. And you'll notice that at the top here, these guys have the highest value, and then it decreases as you go down the table, and actually below this hydrogen ion, it actually switches to being negative. And these guys are very weak oxidizing agents, but very strong reducing agents or being oxidized. So these guys actually want to run that way, whereas the guys at the top, they want to run as a reduction. So making sure I've covered everything. So some key points on this table is that everything's measured in volts under standard conditions, meaning in one ionic concentrations are 1 molar in water at 25 degrees Celsius. Everything is referenced to a standard hydrogen electrode. So it's that idea of where it switches from positive to negative. We've got this one. So everything is measured in relation to this one tendency to be reduced, or the voltage that it can supply. The more positive the reduction potential, the more likely the species will be reduced. A negative reduction potential means the oxidizing reaction is more likely to occur. And again, like I said before, all species, especially all ions, are expected to be aqueous unless otherwise stated. So you'll notice there's a fluoride gas in there. There's a chlorine gas in there, and so when they need to include the state, they will. Otherwise, you can assume aqueous. And then, like I already said, but I kind of got ahead of myself there, the structure of this SRP table, or the standard reduction potential table, is that the left-hand side shows your species gaining electrons or being reduced or acting as oxidizing agents. The higher you are on the table, the stronger the oxidizing agent you are. On the left-hand side, it's often cations or nonmetals, whereas on the right-hand side, it's the species losing electrons, being oxidized, acting as reducing agents. The lower on the table you are, the stronger you are as a reducing agent, or the more likely you are to be oxidized. And these include like a lot of these metals, right? Or anions. So that means, starting with a negative ion and then ending up being something like 0. So just kind of getting comfortable with this horrible chart. Now, those of you who are complaining about how tiny the writing was on our acids bases chart, you're going to be wishing for that back because this is zoomed in. But anyway, so when I'm looking for something as a strength of an oxidizing agent, I'm looking for it on the left-hand side of my chart. So the left-hand side of my chart shows my oxidizing agents, right? My species being reduced. So if I ask you which is the stronger oxidizing agent, nickel or silver ions, you have to find them on the chart. And again, the more you use this chart, the quicker it'll be to find things. But right away, my brain finds the silver ion here at a reduction potential of 0.80. And then I'm looking for the nickel on the same side. So I'm looking for nickel acting as an oxidizing agent. It's down here at negative 0.26. So the silver has more of a tendency to be reduced than the nickel ion. Okay, so now pause the video and give this one a go. All right. I paused the video, but then I got distracted by something. So there's my SN4 plus, and then my SN2 plus is below it. So the SN4 plus is the stronger oxidizing agent. So now let's use the flip side of this table. Let's look for the stronger reducing agent. So now we're going to look on the right-hand side, and the one that is lower on the chart is a stronger reducing agent. So this time if we look for SN2 plus, you're not looking on the left, you're looking on the right. So SN2 plus is one of those elements that can be oxidized and reduced. It's kind of like amphiprotic for my acids and my bases. But we've got my SN2 plus here, and then we're looking for our Fe2 plus on the right-hand side, which is up here. And we would say that SN2 plus is lower down, so it is a stronger reducing agent. And then same thing, we're going to look at chlorine and bromine, or bromide ion, I should say. So there's the bromide there. Now, there's two chlorides. You can't use, like, this is a chloride hydrate, and so don't use that guy. We often call this an acidified species, but anyway, just don't use that. Use this guy. So this one, what is lower, the chloride or the bromide? Definitely the bromide is the stronger reducing agent. Now, just some kind of tips and tricks on this chart. It takes a lot to get used to it and sort of be able to look at it at a glance and figure out where things are. So some quick things to help you: your halogens, your fluoride, your chloride, your bromide are at the top left. So, you know, you've got your fluoride, you've got your chloride, you've got your bromide, which we're often looking for. Your oxyanions are often at the top as well. So you've got this MnO4 minus, this bromate, this chlorate. Anyway, we never have to name these things. At the bottom right is where you're going to find all of your metals. Now, not all of your metals, but a lot of your metals. So kind of down here, we've got lithium, cesium, rubidium, potassium, barium, strontium, calcium, sodium, magnesium, aluminum, manganese. A little bit higher, you've got zinc, then you've got your chromium, then you've got your iron, and it keeps going up. So still cobalt, nickel, tin, lead. Copper is way up here. So these are sort of the exceptions. So some metals appear higher than expected. So copper being up here is kind of unexpected. We'll talk a little bit about copper in a minute, but the fact that there's two copper metals on the right is kind of strange. So there is a note about copper in a bit. But just using this, what would you say, which solid metal has the least tendency to lose electrons? So which metal, looking at this chart, which metal can you find has the least tendency to lose electrons, aka be oxidized? You're looking for a metal on the right-hand side at the top. You do not want it to lose electrons. So the ones at the bottom are the strongest reducing agents. So we're looking for a metal near the top that is going to be oxidized, but it's going to be weak. Go all the way to the top and kind of look our way down. Ooh, there we go. Way up here. We've got this. Does anybody know what that is? Anybody? Sorry, sometimes I feel like the video might talk back to me. This is gold, just so you know. But gold has the least tendency to lose electrons, which is great. Oxidizing can cause all types of problems with metals, one of them being the fact that you're taking something that is solid and making it an ion. So we do not want to oxidize metals. So gold has the least tendency to lose electrons. Which metal has the greatest tendency? That's going to be way down here, and it's going to be your lithium. Lithium is a really explosive metal. It loves to react with things, and so it freely gives off its electrons. All right, so now we're going to talk about these ones that make life more complicated. So that is, some elements have multiple oxidation numbers and they appear multiple times on the table, and some species can act as both oxidizing agents and reducing agents. So the first one we'll talk about, we don't have to talk about all of these, but the first one we'll talk about is copper, because copper is going to come up a lot. When you look at copper, it is at 0.52 and it's also at 0.34. So copper is at 0.52, so there's my copper solid, and then it is also, sorry, that is way too thick. Oh, that's not that. Sorry, I could probably pause the video and do that. Okay, so the copper solid, I just wanted a clean slate. So the copper solid is at 0.52, and then the copper solid is again at 0.34, right? Which is strange. We've also got copper 2 plus appearing more than once on the table. It's here at 0.34, and then it's also right below it at 0.15. Well, that's strange. So let's just take a second and talk about copper. So copper can, like copper the metal, can be oxidized to form copper 1 plus, or it can be oxidized to form copper 2 plus. And then there's this one that we haven't talked about, which is this ion, which can act as both an oxidizing agent and a reducing agent, which is the copper plus. So copper plus is involved in both, like 2 of the 3 reactions as well. So copper solid can oxidize to copper 1 plus or copper 2 plus, and then copper 2 plus can reduce to either copper solid or copper 1 plus. So this leads to an interesting dynamic, which is that copper 1 plus can actually oxidize and reduce itself. So if you see here, this is copper 1 plus being reduced to copper solid. This over here is copper 1 plus being oxidized to copper 2 plus. Because of this fact, copper 1 plus is super unstable. I've got this little note about copper down here. So copper plus is not a species that we use very often, so we don't normally look at these 2 reactions. When they ask you about the oxidation of copper or the reduction of copper 2 plus, use copper solid to copper 2 plus, right? Because of this instability of copper 1 plus. So that's the main thing that I wanted to show you on the table. So this fact that copper solid and copper 2 plus appear twice, and copper plus appears twice, and it can oxidize and reduce itself. So focus on copper to copper 2 plus, unless the question is specific that it wants the copper 1 plus in some way. All right, some other species to be careful of. We've got this chromium 3 plus. It's existing at negative 0.41, and then it's also existing at negative 0.74, so down here. So, copper, chromium 3 plus. Oh, sorry. I was circling the wrong one. There's so many that are duplications. So you've got this chromium 3 plus, which again is kind of strange. So chromium 3 plus can be reduced to form chromium 2 plus. Chromium 3 plus can also be reduced to form chromium. And so, which one should you choose? And the question will be very specific about these kind of strange ones to help you understand which one it's going to be. And then you've also got mercury. Mercury is at 0.85. So up here, you've got mercury liquid or liquid mercury. And then at 0.80, you've got mercury liquid or liquid mercury again. And both of these are oxidation reductions. So mercury can either be oxidized to Hg2 plus, or it can be oxidized to Hg2 plus, which is kind of strange. And then a couple of other ones that can oxidize and reduce, your tin 2 plus, your iron 2 plus, and your peroxide can also act as both. So just be very careful whether it's asking you for these ones. Be very careful whether it's stating that tin 2 plus is being reduced or being oxidized, or acting as a reducing agent or acting as an oxidizing agent, so that you find it on the correct side of the table. The other thing that I wanted to point out is these strange ones which are reactions in acidic solutions. So some reactions require hydrogen ions to be oxidized or to be reduced. So if a hydrogen ion appears in the half reaction, the reaction only occurs in acidic solutions. So for example, if we look at this sulfate reaction, sulfate will oxidize or reduce, in the presence of hydrogen to form H2SO3 and water. There's another example up here of a nitrite ion. There's another number of examples on this chart, especially as you go higher up. You've got this MnO2, this IO3 or the iodate, you've got O2, you've got dichromate. All of these ones, they won't reduce on their own. There has to be hydrogen ions present. And there'll be some tricky sort of multiple choice type questions where like, ooh, will iodate reduce? And you're like, not unless hydrogen's there. And so they'll have to say in an acidic solution or something like that. Okay. The next weird thing is water. Water is found as a reducing agent at 0.82 volts. So there's water here. And then it's a oxidizing agent at negative 0.41. So I'll scroll down a little bit. Water, you know what? Let me just clean this up a little bit. I forgot that I opened it. I paused the video and opened this as PDF because I can hit undo, which makes it really easy to make this a clean paper. So we've got this water at positive 0.82, and then at negative 0.41, we have this water again. And so it's a reducing agent, it's an oxidizing agent. You'll also find it at 1.23, where it's being oxidized to form an acidic solution. And then at negative 0.83, way down here, you've again got water, this time being reduced, and this is in a basic solution. Just to make you aware of it. To be honest with you, I can't think of a single reaction I've done with water because water is confusing. And so we often just don't do half reactions with water. But if you are, just make sure you're looking up the correct water. Is it water in a basic? Is it water in an acidic? It was water acting as an oxidizing agent, or is it water acting as a reducing agent? And then the other thing I've already told you guys is just to be careful with the states. Everything is assumed to be aqueous unless otherwise stated. Okay. Let's use the table. So this question is, I don't know, kind of tricky, but I've done everything kind of up here to help you so you don't actually have to use the table so much. But what we want to look at is, are these ions weirdos, right? Do they only undergo reduction, or do they only undergo oxidation? Can they not react at all, or can they undergo either reduction or oxidation? So let's start with D, okay? Let's look, can any of these ions undergo both reduction or oxidation? Now, the nice thing is I gave you the list here of all the species that can undergo oxidation and reduction, except you have to include water in that group as well. So the only thing, let me just shrink this down so we can see everything. The only species in this list that can undergo both is this guy. So this is D. This is the only one that can undergo either reduction or oxidation. And what I'll tell you is I gave an example of each. So we've already taken off D. So which of these species can undergo reduction? Which of these species can undergo oxidation? And which of them cannot react at all? Well, let's look at the silver plus. Now, silver plus, there's no hint up here to tell you. So let's find silver plus on our sheet. Silver plus is going to be reduced because it's positive, and then it's probably going to go to a metal. So I'm going to look for that silver up here. So silver can undergo reduction. So that's my A. And then zinc is a metal. So metals have more of a tendency to be oxidized. I look down here at negative 0.76. There's my zinc. So zinc is my one that can undergo oxidation. So then sulfate ion must be my one that cannot react at all. Let's just talk about that for a second. What does that mean? Well, the only place that you're going to find the sulfate ion is here at positive 0.17. And it doesn't oxidize on its or reduce on its own. It has to be in the presence of hydrogen. So the reason this is C is because it's missing the hydrogen, or it's missing the word in acidic. right? So they'll say something like in an acidic solution or with hydrogen, and then sure, it can be reduced, but it doesn't get reduced on its own. All right, that was a really long-winded video. Hopefully that makes sense, and then we'll get on to the fun stuff.